Section 5.2 is on proving trigonometric identities. Sometimes we refer to it as verifying the trigonometric identities. We know that identities from 5.1 mean that this function is the same on the left as it is on the right. There are several ways that we can prove whether an equation is in fact an identity. So what we can do, option number one, is maybe we could graph those equations. If they tell us in letter A that we're supposed to check if 3 sine squared plus 2 times the cosine equals 3 times the cosine squared minus 2 times the sine, we could graph those, one equation in y1, the other in y2, and what we would find out would be that once we graph them, they don't actually look the same on the graphs or in the tables, and so we know that those things are not true all the time. In letter B, if we graph the left-hand side and the right-hand side, we're going to look at the graph and see that they look exactly the same as one another, as do the tables, but the problem would be that we can't, of course, check every single value on the graph and every single value on the table. We're only looking at what we see on our little screen there. So that graphing tells us that it may be an identity, but it doesn't let us check all values. So we need another method to determine that. How we're going to do that is we're going to transform one side into the other. So we're going to be given some identities that we're going to try to prove if in fact they are identities. And so we're going to manipulate this equation. We're going to start on one side. You can start either on the left or on the right, and you're going to turn it into the other side. So this is one of the most common and most reliable methods to verify an equation. So let's check out a couple of examples. Example number one, you see listed here. So we have a right side and a left side. So we're going to pick one side to start with. I usually say start with the side that looks like it has more stuff, the side that's a little more complicated. Now, neither of them look complicated, but it sure looks like we have more stuff here on the left-hand side. So if I'm doing my homework, I'm going to start by writing out the equation that is on the side of the equation for the identities here that I want to start with. So I want to start with the left-hand side, and I'm going to turn it into the right-hand side. It's important that you notice that we're not working with both sides at the same time. A common mistake is that people would want to take this cosine and multiply it over to the other side. I cannot do that when I'm trying to verify, because verify says, show me that the left side is equal to the right side. If it wasn't equal, I wouldn't be able to multiply that cosine over. So you can only work with one side and then switch it to the other side. All right, so once we write down the side that we're starting with, then we're going to say, well, what can I do based on the identities that we know from section 5.1? Do I have any reciprocal identities, any quotient identities, any Pythagorean identities that I want to know? Remember that you had your list of the 5 strategies that you might use to simplify. Verifying identities is basically simplifying them, except for now they're telling you what the answer is supposed to be equal to. So in the end, I know that I'm going to end up with cosine plus tangent. So it's just like simplifying, except for they're telling me what the answer is. Okay? When I think of those strategies, first strategy was change the sine and cosine. Second, use Pythagorean identities. Third, factor something out or distribute something in. Your fourth was to use a common denominator. So when I think about those strategies, and hopefully you have your sheet in front of you, which one are you going to want to use? Everything looks like it already has sines and cosines, so that first option probably isn't going to work out for us. I do see a Pythagorean identity in here. You see that in the numerator, I have a 1 and I have a minus sine squared. So this is why you want to memorize all of those identities, especially the Pythagoreans, which aren't as common to us. We had the cosine squared plus the sine squared was equal to 1, if I just write that off to the side. And so if that was one of our Pythagorean identities, 1 minus the sine squared, when I subtract that over, those two together are going to be equal to the cosine squared. And when I replace with the cosine squared in the numerator plus the sine, all divided by the cosine. So that's what I have so far. Now look at what our final answer is supposed to be, cosine plus the tangent. I still have to show the work how I get there, but sometimes we can use that to give us some ideas for what we might want to use next. When I have the cosine plus the tangent, let's check out this fraction. Think of what's going to happen if I take cosine squared over cosine. I think I'm going to get the cosine. What about sine over cosine? That is going to give me the tangent as well. So this looks like it's going to work out for us. How am I going to show that? I'm going to split up this fraction. So this falls into the common denominator category. In this case, it already has a denominator that's in common. So when that's true, what I can do is I can split up that fraction. So this falls into the common denominator. It's already common, so let's break it up instead. And now my last step for us that you would just keep writing below on your paper here, cosine squared over cosine is equal to the cosine, and sine over cosine is equal to the tangent. There you go. Isn't that fun? Perfect. All right, so that is our verification of our first identity. Let's check out the second one. Sine over 1 plus cosine equals 1 minus cosine over the sine. Go through your list of those strategies again. Change to sines and cosines already there. Pythagoreans, no, that's nothing squared in there. Factor something out. Neither side looks like it has a common factor that I would be able to use. Or something to distribute in. Common denominator, I'm not sure if that's going to work out on either side there either, since I have nothing to really split up on the top or the bottom, depending on which one I choose. All right, well, now is where your fifth strategy comes into play, and option number 5 for that strategy is going to be to multiply by the conjugate. The conjugate, remember, says that you've got the same terms with the opposite sign on the inside. And so let's say that I'm going to start with the left-hand side again, though I could start with the right-hand side in this question just as easily. They both look about the same as I'm starting. So I write down the side that I'm starting with. Remember, that means that I'm trying to turn it into the right-hand side. The conjugate, by that I mean this was 1 plus the cosine, so I'm going to multiply by the conjugate, which is 1 minus the cosine. I'm going to multiply by that in both the numerator and the denominator of my function. Now, why would I want to do that? Let's look at what we end up with once we do our distribution. On the top, by the way, I'm not actually going to distribute the sign. Why am I not going to distribute the sign? Because I can see in the final answer, I want to have 1 minus cosine in my final answer. So I don't want to actually lose this or break this apart because I need that in my final result. So I'm going to leave this as sine times 1 minus the cosine. I can always distribute it later if I decide that that's helpful for me. But since I know I need that kind of by itself in the end, I'm not going to distribute through. Now, check out the denominator. This is the important part for why we decided to multiply by the conjugate. First terms give me 1. A conjugate is really a difference of squares if we think about it. So our outside terms and our inside terms cancel each other out all the time in the conjugate. So we have a minus cosine of x and a plus cosine of x. So those disappear. And then our last terms together, last terms multiply to a minus cosine squared. So that's our distribution when we multiply by the conjugate. Now, what can we do next? When we use that conjugate, you should notice something about our denominator, 1 minus the cosine squared. If you're looking at your identity sheet, that should remind you of a Pythagorean identity. And we know that the denominator, I'm going to rewrite the numerator here quickly for us first, that the denominator of 1 minus the cosine squared is going to be equivalent to the sine squared. So we use that Pythagorean identity in there. And once I do that, now what simplification can I do? And again, all the time I kind of like to look at what's our end goal, 1 minus cosine over the sine. We'll look at that. We've got a sine squared on the bottom, so we're getting close. A sine on the top, sine squared on the bottom. So I can get rid of one sine in each of those. And that's going to leave me then with 1 minus cosine in the numerator and a sine in the denominator, which is exactly what you were looking for. Isn't that great? So that's how we verify example number 2, and we had to multiply by the conjugate, and then we also used some Pythagorean identities in there as we were trying to solve. Now, how would you know when to multiply by the conjugate? You're going to use a conjugate, especially in those cases where when you multiply by the conjugate, it turns into something from a Pythagorean identity. So you might see this when you have like a secant squared minus 1, for example, also would be something where you're going to have a trig identity. So maybe you have secant minus 1 and secant plus 1. So check out all of those that are going to have a Pythagorean identity to know when it would be best to multiply by the conjugate. Example number 3, again, starting with the side that looks the most complex. That means that we're going to start with the left-hand side. It just so happens to be the left-hand side in these examples, but when you get to your homework, it could be either side, whichever one that you decide you want to start with, but it would seem obvious that I can't start with the sign and know where I'm going to go to. It's easier to condense things down than to split them up. So I guess if I'm going through my list, I have 2 options. Option number 1 was to change to sine and cosine. I could change these first 2 terms to sines and cosines if I wanted to do that. Option number 2 would be maybe to distribute these together. Those are the main 2 things that I would see out of our list of 5. There's no Pythagorean identities. There's no common denominators. Doesn't look like I would maybe want to use the conjugate yet. So we can decide which one that we want to do in this question. And the trick that I usually tell people is if you see 2 options, you're not going to know what's best until you do it, so it just takes practice. And if you see 2 options, chances are you're going to use both of those things. So we could change to sines and cosines first, but then we're going to end up distributing after that. Or we could distribute first, and then we're going to change to sines and cosines after that. So it's completely up to you what you might choose to do, and it just depends on whichever one seems easier to you at the time. All right, so let's say that I decide, what do I want to do here? Maybe I'm going to change these to sines and cosines in the expression first before I distribute. So that would give me 1 over the sine. The cotangent is cosine over the sine. And then we're going to leave this one because it's already in terms of sines and cosines. Now, before I distribute them together, what I'm going to do is I look in this first set of parentheses and I see that they both have a sign as a denominator. So it's like a common denominator just came to us and we didn't even have to do that much work to make it happen. So I'm going to rewrite this as 1 plus cosine over sine times 1 minus the cosine. All right, so now since I changed to sines and cosines first, now I'm going to have to distribute as my next step, instead of the reverse of that. Now remember, when I distribute, if I'm multiplying fractions, I multiply the tops and the bottoms, and the second term really has a 1 in the denominator there. So now as I distribute those together, oh, look at that in the numerator, 1 plus cosine, 1 minus cosine. When I distribute those 2 binomials together, I'm going to get a 1 for my first term. The outside and the insides are going to cancel out because these terms are conjugates of one another, and then I have minus cosine squared. You should already be thinking about what 1 minus cosine squared is going to give us. We still have a sine in the denominator. And then 2 more steps, I guess. 1 minus the cosine squared, what's that equal to? You should be thinking of that as your Pythagorean identity. So that's going to be equal to the sine squared divided by the sine, and then my very last step, sine squared over the sine, simplifies to the sine. Isn't that fun? It's kind of fun, just kind of just like a puzzle that you're working through, saying if I gave you just the left-hand side, it's not obvious that it's equal to the sine, but just through that series of rewriting and reworking, we can simplify that all the way down to the sine. This is one of my favorite sections because it's kind of just like a puzzle and putting all of those pieces together. All right, last example for this section, tangent plus cotangent equals secant times the cosecant. We need to figure out which side seems more complicated, and neither of them, again, seems complicated, but we have 2 terms in the first side. On the left-hand side, tangent plus cotangent counts as 2 terms. On the right-hand side, secant times the cosecant. When 2 things are multiplied together, it really only counts as 1 term. So that more complicated side is going to be the tangent plus the cotangent. And then if we run through our list of our options for our strategies to simplify or to verify an expression, how are we going to get this equal to the secant times the cosecant? We'll run through that list. Can I change to sine and cosine? We could. Pythagorean theorem, Pythagorean identities, nope. Factor something out or distribute something in, nope. Common denominator, no denominators there. Conjugate doesn't look like it's going to work either. So as I'm going through my list, changing to sines and cosines seems like my best option here. So the tangent is the sine over the cosine, and the cotangent is the cosine over the sine. So again, sometimes you don't really know where you're going to end up as you go through this question, but you just have to say, what can I do? And then when you get to the next step, we're going to ask that same question. What can I do? Okay, well, I just changed everything to sines and cosines, so that's out. Pythagorean identity, still nothing is squared, still nothing in common to factor out or distribute in. Ooh, but now I have a fraction, so I suppose I could make a common denominator, and there's still no conjugates there, so a common denominator is going to seem like my best choice for the next step in here to change that into secant times the cosecant. Now, if I make that common denominator right now, they have nothing in common, so that means that I'm going to multiply this first fraction by sine in both the numerator and the denominator. And that means my second fraction is going to get multiplied by the cosine. Now we created a common denominator, so I'm going to write out the denominator first. My denominator is going to be cosine times the sine, or maybe you wrote sine times the cosine. It doesn't really matter. I just did cosine times the sine since that was in my first fraction. What do I have in the numerator? First one has sine times a sine. That's going to give me a sine squared. And second term, cosine times, oh, cosine squared. Hey, that looks like magic on the top. Sine squared plus cosine squared. What do we know about that? Sine squared plus cosine squared is 1. Favorite identity there. So we've got the cosine times the sine in the denominator and a 1 in the numerator. And again, looking back to our final answer, we're supposed to get secant times the cosecant. So how is that going to happen? Some of you might be seeing it right now. For some of you, because it's multiplication, you might like to split that up. That's the same as 1 over cosine times 1 over the sine. Because it's multiplication, we're multiplying the top, we're multiplying the bottom. That gets us to our final answer there. 1 over cosine is the secant of x. 1 over sine is the cosecant of x. Lo and behold, gets us to our final answer there. Look at that. So we have just verified example number 4. And again, the main thing I need you to think of as you're going through these questions is that some of them in the book, it always seems easy when I go through them together here with you, but when you get to your book questions, you might seem like, oh my goodness, this is hard. Every single one is a different question. Every single one has a little bit different strategy, and you might have a different strategy than what your friend has, and they both could work out just fine. And it just takes time to practice and see what's happening there. So work through them, do your best to go through and see what you can do. And just like this question, it might not seem obvious how you're going to switch at first, but just think through which strategy can I use, give it a try, and see what happens from there. Go ahead and look at your section 5.2 book homework.